Well, good afternoon. This is our fourth plenary speaker. His name is Bilong Liu. Dr. Bilong Liu is now a professor at the Qingdao University of Technology, China. He has more than 20 years of experience on vibroacoustic research after he completed a bachelor's degree in physics. He received a PhD in acoustics at the Institute of Acoustics Chinese Academy of Sciences in 2002. Then, he worked on noise transmission of aircraft plates at MWL, KTH, Sweden, and received another PhD in applied acoustics from KTH in 2006. From 2007 to 2017, he has been working as a research professor and leading the group on acoustical materials and structures at the Institute of Acoustics. Dr. Liu has completed over 20 projects for industries and the government, have authored and co-authored over 100 journal papers, conference articles, and 3-volume monograph of vibroacoustics. He was honored as Distinguished Professor of CAS at 2015. His main research interests are acoustical materials, structural noise and vibration, noise induced by fluid structure interactions, underwater acoustics, active control of sound and vibration, simulation of acoustical devices, and so on. So it's a lot of stuff.
So thank you very much. Time to work. Okay. So dear colleagues, and good afternoon. And my topic is noise transmission and absorption of lightweight structures. So why lightweight? Because nowadays we want to reduce the noise, but we don't want to increase the weight or the thickness of the structure. And the outline is like this. So first I would begin with the introduction of the engineering requirements. Afterwards, I would talk about the sound transmission of lightweight plates. Then I will talk about sound absorption of resonant structures. And finally, I will give some conclusion. And in the end, I will give some few slides about Ernst Lears, and I would give some memory to him. Okay, if you look at typical noise spectrum in the aircraft, you could see the noise energy actually is from 100 hertz to 1 kilohertz. Actually, this noise spectrum is measured by myself during flight. And also, if you look at this high-speed trains, and you could see 60 hertz and 600 hertz, the noise energy dominates. And also, you may notice that the noise level inside a high-speed train is much lower than the airplane. That means acoustically, it's much comfort in high-speed train than in the airplane. So that might be the reason nowadays Chinese they prefer to take a high-speed train rather than aircraft. And also, if you look at the automobile, so inside the automobile, it's 100. The noise energy is 100 to 300 hertz. And for example, for a transformer or shunt reactor, and it's 100 and it's harmonic components. So it means usually 100 hertz and 200 hertz tone noise dominates the noise energy. And also, if you look at these underwater vehicles, usually for underwater vehicles, you have acoustic layer. So the thickness of this layer is about 5 to 10 centimeters. But they want they wish to absorb the noise, the wavelengths of 3 meters to 5 meters waves. So it's a very challenging problem for acoustician, actually. So in summary, so the key issues in this topic is how to improve the low-frequency sound insulation and absorption without increasing the weight or thickness of the structure. That's a key issue. And the solution is that we all know for high frequency noise, we could use material. We could use good material to reduce the noise. But for low frequency noise, using material is not enough. So usually you rely on, you have to find very innovative structures. So we will take the first problem that the sound transmission loss of lightweight plates. So lightweight here refers to very thin plate for aircraft fuselage, for example, or sandwich plate for vehicles. And for this kind of plate, for a sound transmission loss, the well-known is a mass loss, so-called mass loss. The mass loss means a doubling of the mass or frequency at 6 dB to the sound transmission loss. Actually, for a thin plate, the frequency range of interested is always lies in this mass loss range. So this means to improve transmission loss without increasing the weight seems an impossible task. Impossible. But human never stop the foods. So in 2000, there was a very famous paper published in Science. And in this paper, the concept of this so-called sonic crystal is introduced and set off an upsurge for a study of acoustic metamaterial. So the concept, the core of this structure is quite simple. It's basically it's a lead ball. It's a very heavy ball, and wrapped by this rubber, and to form a damped mass spring unit. And the unit was periodically arrangement, and to have this kind of structure. So at a certain frequency, you will have resonance. At the resonance, you will get acoustic energy dissipation or diffraction, some waves diffraction. So, but the result is measured in the impedance tube. Impedance, it means it's only lumbar incidence. So afterwards, many workers published in the journal. So all sorts of similar sonic crystal proposed. For example, from this soft ball and to this cavity resonance, or to this membrane and mass resonance, and so on and so on. But all this work is simulated or measured in this impedance tube. So if you look at these measurements, standard laboratory measurements for transmission loss, actually they have A and B is for large sample. So it's used like you could use 2 reverberation room or use 1 reverberation room and mostly anechoic room using this called sound intensity method. And also for this impede tube, you could measure this normal incidence transmission loss, but this kind of measurements only valid for soft sample, not valid for very hard or stiff sample, such as like plastic or wood or mechanical plate, because when this very hard sample is very small, then what you measure is a boundary effect, not the structure itself. So there was paper once mentioned. So with this kind of structure, it's honeycomb sandwich plate, and it could improve the sound transmission loss significantly in the low frequency range. But this, what is measured is in the impedance tube. So another paper, they commented that is not possible, because if the plate is large, then the sound transmission loss is not high at all. So impedance tube does not valid for these hard samples. So we must be aware of that. And also, this kind of resonance structure is memory and mass, and they try to improve the transmission loss for aircraft side plate. But this work is also simulated in impedance tube. It's normal incidence. But quite recently, during communication and researchers from this Fraunhofer Institute Building Physics, they tested 8 square meters layers based on resonance. Actually, it has some good results, but a very narrow band. For single layers, it's good. But when this layer was put in between skimmed plate and trained plate, the results is not so evident. So I think they are still going on, working on that, but I don't know what's going on there. Okay. Another result is also for large aircraft plate, just published in 2019. Actually, you use this small units to generate some kind of resonance, and they attach this kind of resonance to the aircraft plate and to absorb the plate vibration, the plate resonance. Okay, it does work. It does work. So in this frequency range, it is improved like 6 dB, 500 hertz to 800 hertz at ring frequency range. So it does work. It worked. But still, the total mass added from 5% to 85%. So for total mass. But if you look at the skin plate only, so not ring stiffener, no stiffeners, and this added mass could be the 25%. So it's not a mass added. But this is a very interesting results. And also, after I talk about how to improve the sound transmission loss, then I will talk about reliable prediction tools for sandwich plate. So for sandwich plate, they have very advantage of no weight and high static stiffness. But they often poor acoustic properties if designed improperly. And for sandwich plate, I must mention the Leerson's work and the equations derived based on Hampton's principle. And he derived these 6 odd equations. So with this equation, you could have this 6 odd dispersion equation. You could have 3 waves. And the most important wave is propagating fracture waves. It's a solid line. And actually, the property of this kind of waves, due to this kind of properties, the bending stiffness of this sandwich plate actually is frequency dependent. It means at a very low frequency, it's very hard. Because you have to bend the entire structure. But when frequency goes high, it drops quickly. And in the high frequency range, then the bending stiffness of the plate approach to the face plate. So that means this kind of structure has very important properties. That is called high static, no dynamic stiffness structure. So this is actually it's very important properties, because if you design isolates, you need this kind of properties. Or if you want to design an absorption layer underwater application, you want this sort of properties. So the sandwich structure basically have this sort of properties. It's called high static, no dynamic properties. Also, Leerson, he gives the predicted and measured loss factor for a typical sandwich plate. And but this, you could see the measured results has variation, and also loss factor of sandwich plate is more complicated than isotropic plate. So actually, unlike an isotropic plate, single plate, the predicted transmission loss of sandwich plate are very sensitive to this loss factor. So actually, not the loss factor of the structure itself, but also the loss factor due to the sound radiation. But currently the method for measure this loss factor is not accuracy enough. And also currently they published a lot of paper on analytical words, but not method for our method data, measured data for this loss factor. So therefore, I think accurate method for measurements of effective loss factor for sandwich plates in a wide range of frequency is what's to be invented. Okay, nowadays also engineers relies more and more for commercial codes. For example, for this is a comparison between this Voix FEM and the model summation method for transmission loss prediction. So you could see there's a variation in a very low frequency range. So the commercial code it not always give you correct results. So you must have something for a reference to make sure what you get is right. So why this commercial code is not correct, or in some frequencies it's not working? If you look at his documents, and actually for this, actually in virtual lab, actually they assumed that the transmitted wave propagating the same as the incident wave. This is correct for infinity plate, but for finite plate or ribbed plate, due to this scattering of the sound, it might be not correct. Maybe in some frequency is not correct anymore. So that might be reason. Maybe other reasons, but I guess that might be one reason. Also, and apart from that, I will talk about the plate and due to the typical excitations. So we must be aware of that. Difference could be huge for the noise transmission of the plate due to the, for example, acoustic diffuse field excitation or turbulent boundary layer excitation. So here is an example. So we had a plate. If we had a plate and airflow over this plate, and if we take this stiffener into account, or we don't take this into account, then we get sound radiation power is quite different. So actually, this is verified by a wind tunnel test. And we had this stiffener here, which are normal to this airflow. And you could see the plate response with and without these stiffeners is almost the same, but the radiated noise changed. And also you could say if this stiffener is parallel to this flow, then the plate response and radiated sound is almost the same. So this actually is quite interesting. And also, if you put a damping layer on this plate, and you could see the plate response dropped significantly. Also, the noise level also dropped as well. The sound power also dropped as well, but not so effectively. That means if you put a damping layer on this plate, it means you increase the sound radiation efficiency. So we look into it in detail, and we checked this very famous book, Struck-bound Sound, in 1982. So actually, they had a formula for this infinite plate, or you could say for very large plate. And the radiation efficiency for an infinite plate, he don't take this damping into account. So which means below the critical frequency, so the bending waves, they don't radiate sound. But if you take damping into account, then the radiation efficiency has a relationship with the loss factor. Actually, it's quite straightforward. So if you increase the loss factor, if the loss factor is doubled, then the radiation efficiency increased 3 dB below critical frequency. And for a finite plate, it's also if you increase the loss factor, it will of the structure, it will increase the radiation efficiency of the plate. But it's more complicated. So in compare with a very famous Lipington's formula, the loss factor actually increase 5 to 10%. If the loss factor increases 5 to 10%, the radiation efficiency may increase 4 to 6 dB. 6 dB. The reason behind this could be quantitatively explained. If there is no damping, so the fracture waves may propagate with constant amplitude. That means the waves, the air volume being pushed forward and being pushed backward are equal, and can be counteracted. But if there is damping on this structure, then the fracture wave is decaying with the distance, which means the air volume being pushed forward and backward are not equal anymore, and that caused sound radiation. And also we consider the airflow. If there is airflow over this plate, and the radiation efficiency actually increase with this flow speed. This is quite interesting, actually. So the reason is that at high flow speed, the radiation efficiency of hydrodynamic coincident modes are much higher than that of the low speed. So for turbulent boundary layer excitation, they have this kind of hydrodynamic coincidence. So at this specific point, the plate will be highly excited, will be strongly excited. So those excited modes, actually, if at a high speed, actually they have very high radiation efficiency. So it's quite interesting. And also, if we take damping and flow speed into account, take both into account, we could find a very interesting things. So if the Mach number is very high, for example, 0.27, then the increased loss factor actually is below certain frequency is much higher than that of Lipington's formula. What you get is much higher than Lipington's formula. So if you use Lipington's formula to for this high speed plate vibration on the high speed excitation, airflow excitation, it might be not correct. Will be have big error. Okay. So the second large question is on sound absorption. So for sound absorption, conventionally we use porous material for sound absorption. And for porous material, there was a very famous, and actually it's called DB model. This model. And actually, this paper was cited, if you put it on the Google, it's cited over 1,600 times. So it's a very huge number in acoustic society. And this model is quite simple because if as soon as you get this flow resistance, you could calculate the sound absorption coefficients very accurately. But still, why still you need relevant structures? Because the porous material are not always applicable in some cases. And also to absorb low frequency noise, a thin layer of porous material is required. So if we look at this this formula for sound absorption coefficients, then to achieve high sound absorption, you need real part of this impedance to 400 in air. And the imaginary part should be approach 0 or as small as possible to achieve very high frequency. So that means you need resonance to achieve that. But the increased resistance to 400 is not so difficult actually. It's not so difficult. But reduce the acoustic resistance in wide frequency range, this is very difficult. So this is a very famous, very successful actually is resonant structure for sound absorption. It's so-called micro-perforated plate. And it was successfully used in German Bundestag in Bonn. So the secret of this kind of structure is that so away from this resonance, unlike Helmholtz resonance, the acoustic reactance of MPP increases slowly to ensure the value is smaller than that of acoustic resistance in a wide frequency range. So this guarantees this broadband sound absorption of the micro-perforated plate. So this is a very important feature of the micro-perforated plate. Okay. So the benefit of this micro-perforated plate is can be easily designed to have low frequency and broadband sound absorption. So you could see here, compare with this porous material. And but if you want my MPP have the best sound absorption, the diameter of the holes should be 0.1 millimeter. And the thickness of this plate usually is 1 millimeter. That means the cheaper perforation technology is not available. So that means cheaper perforation technology is worth to be invented. Or alternatively, new absorption structures with big aperture or better sound absorption structure deserve to be invented. Okay. And this is MPP and some kinds of extended structures. So here you could see they use a separate cavity with separate cavity and different cavity depths, and to broadband this sound absorption. Then because they have multiple resonance. And also they combined MPP with Helmholtz resonance, and to have another peaks in the low frequency range. And this is a perforated plate, and combined with wire mesh, and to achieve the similar performance of MPP. As I said before, so for the micro-perforated plate, the hole is too small to be produced massively in a cheap way. So we want to have something. I mean, the hole is much bigger. So this kind of structure is called a perforated plate with extended tubes is introduced. So here you have this kind of sort of extended tubes. Actually, because the hole is large, so you need to increase the length to increase this acoustic resistance. Actually, this structure works in the low frequency range. So for example, if you want to absorb 300 Hertz, the MPP might requires 10 centimeter cavity depth. But with this structure, you only need 5 centimeters and have similar absorption coefficients, performance. Okay. And this is also the extent of this PPET. So you have this typical structure, but combined with this porous material, you have this extend this absorption bandwidth. And also this is measured in the reverberation room with 10 square meters. So for diffuse field incidence. And this one is just a new one. So because the extended tube is still complicated. So in this paper, we use this zinc plate and with perforation with big holes and to achieve the similar results. Okay. And this picture also shows perforated plate, but actually it had grazing flow over it. So it works in the low frequency range. It works. It's single layered and double layered. Actually, this kind of structure has been used for big wind tunnel noise reduction already. Okay. So we also want to talk about another kind of the structure. It's called a semi-active structure. The semi-active structure is the most, I think, most promising structure is called shunted loudspeaker. So why shunted loudspeaker? Because the loudspeaker can be massive produced and can be very cheap. And also, this result is a micro perforated plate and shunted loudspeaker in series connection. And this one is in parallel connection. And this is a result for multiple shunted loudspeakers. And you have several resonances, so you could broadband the sound absorption. And the very interesting part is that just quite recently, the group of Professor Huang, they proposed the concept of this so-called acoustic switch. Why call it acoustic switch? Because he can achieve the sound absorption at any frequency with this structure. So it can be very useful if you, for example, if you want a specific impedance in some case. So this, I think, is a very interesting part. And also, they had a very fascinating results just published in 2019, actually. And they achieved, with this shunted loudspeaker, they achieved broadband absorption with thickness of 6 centimeters. So this is not easy. If this, because this is a small sample, if they had like 10 square meters results, it could be very interesting. Okay, so I will talk a few slides about the other resonance structure. So this one is a membrane and mass actually is iron. They had this membrane and iron and try to generate resonance and to become sound absorption. But I don't think this kind of structure is easy to be handled in practice. Because this kind of structure, they also need this cavity as well. And also the parameter of this kind of structure is very difficult to be handled in practice. Okay. The solid crystal, as I said before, is still difficult for sound transmission loss or sound absorption in the air. But very interesting thing is that if you use it for a water application, it can be very efficient. So here is an example of this structure. It's called sonic crystal. It had steel core and soft coat rubber and resonance. And if you put it on the water, it's very good for sound absorption in the low frequency range. Okay, so I have some summary. So for the sound insulation of lightweight structures, resonance-based approaches are still difficult in practice. We must be aware of that. And also, methods based on Hampton's principle or model summation method are reliable and could provide a reference for a prediction for sandwich plate or more complicated structures. And also, we should be aware of the difference of vibroacoustic behavior due to different excitations. And also the damping treatment increase radiation efficiency. We must pay attention to that. So also accurate measurements method for loss factor is what's to be invented. That's commands for sound insulation of lightweight structures. And for sound absorption, resonance-based approaches shows very great potentials. So in compare with the MPP mic perforated plate, it might be possible reduce the cavity depth from 10 centimeters to 2.5 meters, 2.5 centimeters, but has and have the similar acoustic performance. And also underwater application, possible 500 hertz waving using like 10 centimeter acoustic layers to absorb 500 hertz noise. So that must also based on resonance approach. And also possible large and thin samples of shunted loudspeaker for broadband sound absorption. That could be also possible. Okay. And finally, I want to show some slides in memory of Professor Anders Nielsen. Anders Nielsen was a chaired professor at KTH and also the founder of the NWL is Max Wallenberg Laboratory for Sound and Vibration. And actually, in 2003, ICSV10, he hosted this conference in Stockholm. At that time, I was a PhD student in NWL. And also, you could see at that time, Professor Crocker is still very young. When he was in duty, so he's very busy, Professor Anders Nielsen, very busy, so he has to maintain a relationship with the industrial partners to find the funding for this laboratory. But after he retired, he is very energetic and concentrated more for scientific works. So in 2015, from 2015 to 2016, he had these 3 books, 3-volume books published. And I, as my knowledge, so some university uses this kind of book to give lectures for graduate students, or reference book for graduate students. And also in 2018, the year he passed away. Actually, he had 3 papers. And this year he had 3 papers published. And this paper is actually the last paper he published. Just before he passed away, he was informed that this paper was accepted by JASA. So thanks JASA very much. He was very content about that. And this message actually is the last message he sent outside. After that, he was too weak to send anything outside. So this message is give a talk in Montreal, talk about a sandwich. That is the last message. And also he loves this Max Wallenberg Laboratory for Sound and Vibration, NWL, very much. So in 2017, they had celebrated 40 years celebration. So he was there, and I think he was very joyful to be there, because afterwards he sent me a very long letter, and write down his joyful moods and delightful moods. So he is very great fun to meet and talk with old PhD student. He knows them very well. This photo is taken, now it's 1987. It's 30 years ago before this celebration. But now it's 32 years ago. So at that time, he just have this chair professor at KTH, accept this chair professor at KTH. So this photo was taken in outside of Stockholm in summer house. Okay, actually, personally, I like this photo very much, because in 2017, my new group also have 9 persons. So I want to make a copy of this paper, make a copy of this photo in Qingdao. I want to make a copy of the photo. But then he sent me a message and tell me a story, everyone about this in this photo, especially this person with the life. This person, the PhD student with life. He said after he got his PhD student, he became an associate professor in the university. But afterwards, he was suicide. Actually, his mother and his brother also suicide. So also killed themselves, but not at the same time, but maybe a couple of years, something like that. So I think this is a very tragic story. I don't want early graduate student to carry this curved lives. So finally, I had this photo for my group. So no one carry these lives. It's not okay. But in the in 2000 end of last year, 2018, we have almost 30 pupils. So I wish in some day we could have numbers similar to this NWL for sound and vibration research. And finally, I wish to end up this presentation with this photo. This photo actually was taken in outside of Imperial College in Beijing. And this statue is Confucius. And because Ernst likes this photo very, very much, so he presented this photo in many times during his presentation. I think he likes this photo very much because he likes Chinese philosophy very much, very much, and he respects Confucius very much. I think that might be the reason. Actually, he read a lot of Chinese philosophy books, so very interesting. So personally, I want to thanks to this Ernst Nielsen. I wish to could able to talk to him again, maybe in another space time. And also, I wish to thank him very much for his contribution to the Acoustic Society. So that's my presentation. So thank you very much.
Thank you, Bilong. Is there any question? You can maybe use the microphone.
Well, it's a bit difficult to switch over to technical questions after
You mean
your kind words about Anders, but I was a little bit wondering about
here?
the effect of damping on the radiation efficiency.
Yeah, you mean this, much previous? Okay.
Well, your explanation about the effect of damping on the radiation efficiency was very much appealing to me. That's exactly that slide over there.
This
Well,
go on.
you had a nice explanation about the
Oh, this one.
the,
More.
the point I wanted to ask you is the dependency of damping on the radiation efficiency, is that dependent upon the type of excitation? I mean, if you have a point excitation, I can imagine that if you have damping, that you have better sound radiation. But is that also the case when you have a distributed load, like diffused field or such thing? Because then the vibration level is everywhere the same because you have a distributed load.
So sorry, I don't understand your question. Okay.
Can you maybe go to slide 28, I think it is.
I know you want to ask about
This one, 28.
This one.
28, that one. This is a nice explanation.
This
of
one.
28.
28. Okay. This one.
Is a nice explanation why damping
Yes.
increases radiation efficiency.
Yes.
And if you have a point excitation, I can imagine this, the bottom situation will occur. But will that also occur when you have a distributed load over your plate?
So actually, yes, a good question. Actually, this is only very quantitative explanation. The real situation is more complicated. I mean, this actually is like a reflected wave we assumed. So there is no excitation at all. We just assumed this, if there is bending waves, so if there is no damping, then this is almost the same amplitude. But if there is damping, then it could be larger than this, and this could become radiated sound. So, but with the excitation, it could be more complicated. Yes, I couldn't explain it actually.
You have the same effect if you have distributed.
Distributed. Sorry.
You have the same kind of effect if it is a distributed load. It's not only occurring when you have a point load. That's what you're saying. Is that true? Okay.
I don't understand. Sorry. Anyone can explain a little bit more?
No, relating to what Bert said, I think my understanding is that the example you are using here is a propagating wave, right? So your wave starts from one place and ending up with the other in the way that you have damping, so that's why you got attenuation in amplitude. So you lose the symmetry, right? So this is the radiation, mechanism. But if you have a real structure and you have finite size,
Yes.
and you have excitation that you're going to look at a standing wave, right? And the standing wave that you don't have necessarily this mechanism. So I'm not sure that the damping always increases the radiation efficiency if you have a force vibration problem.
Yes, I understand. Yes, it's for inflated plate, and you could explain like this. But in real case, it's more complicated. It's for finite plate. You have standing waves. So I guess it still have this sort of effect, but it's more complicated. So that's the reason. Compare with Lipington's results. Compare with the Lipington's results. It's not 3 dB when the loss factor doubled, so it's more complicated. More complicated. Okay. So we had some modification to this Lipington's formula. Sorry. Okay. I hope I answered your question. Okay.
So you mentioned the acoustic switcher.
Acoustic switch. Okay.
Yes, of sound. Can you elaborate a little bit about it?
About it. And what do you want to know for this acoustic switch?
I just wanted to know how it works. I could not grasp it. And
because with this shunted, this circuit, they could introduce additional, they called reactance. So this selective reactance plus the reactance of the structure, it can be you can design to achieve this zero at early points, early frequency. That's the idea, because you have with this shunted circuit, with shunted loss peak, you introduce additional reactance. Actually, it's selective, so it's varied with parameters of like resistance or other things. I have this person's WeChat. If you want to know more, you could. I could give it to you. Okay. Okay.
Also at page 28, in here, this is I still question about this. Why the damping increases, the radiation efficiency also will increase. I think not always true in this case, because in measurement in the mold shape, if we add some damping, for example, laminate plate or the sample plate, the mold shape basically is symmetrical. But in this case, in your case, I think in page 28, there is the plate is no more symmetrical. I don't think this always.
You don't think it's not always?
Yeah.
Yeah, for damping treatment, increase sound radiation efficiency.
Yeah.
Yes, what we done? We just like do calculation for limited plate. Actually, we couldn't say it works for all plate. It's not work for all. It maybe work for all plate, but what I have done is only for limited plate. But for infinite plate, it should be correct, because sorry, let's say this one. Because this formula is correct.
So
this supposed should be correct.
So it means basically for infinite plate it's
So
working.
So for infinite plate, it means the radiation efficiency should be how to say it? It should be has relationship with this loss factor directly.
I mean, in page 28, do you measure this mold shape, such kind
it's
of? It's
not a mold shape. It's actually it's a banding wave, radiation of a banding wave for infinity plate, because if you have this, you assume these bending waves, then you got the sound radiation, then you had this kind of radiation efficiency. But for finite plate, it's more complicated.
Okay, thank you.
Okay. Okay.
There is another reason also why the damping affects the radiation. For a point excitation, you get near field radiation from the point or line connection, and then you also get radiation from the propagating waves that are going out, and also once they're reflected. And the damping loss factor affects the ratio of the power that's radiated by the near field and the power that's radiated by the resonant field. In the case of a diffuse field, you also get a difference because you have radiation from the forced waves, and you also have radiation from the freely propagating waves once the forced waves are reflected at the boundaries, and the damping loss factor changes the ratio of those two lots of ratios. So there is another reason also why you'll get an effect of the damping loss factor.
Actually, I didn't see in the calculation, I didn't distinguish how to say it. I didn't take this into account, the difference between relevant or forced. What we calculate actually is, what we assumed is like as a Lipington's excitation, every mode was excited equally. It's like rain on roof excitation. So we get this kind of results. It's the same as the Lipington's assuming. So we didn't see any difference. I mean, we didn't distinguish this what is relevance or what is forced.
But it is important to it does make a difference on how it's excited, and Lipington's one is definitely for freely propagating or standing waves that are for a simply supported finite panel. But for other situations, for below the critical frequency, then the force wave radiation efficiency is the most important parameter. But you also get both. You get radiation from the force waves, and you get radiation from the resonant reflected waves.
Okay.
But a very interesting paper.
Okay,
I enjoyed it. Thank you.
Thank you very much. Thank you very much. Okay.